Hello everyone, my name is Mitali. I am All India Rank 25 in CSE GATE examination. Previously, I worked in MNC as backend developer. I like teaching, so I shifted to teaching from last 3 years. I taught approximately 30 batches. So the first question is, the following functional dependencies are given, and the dependencies which are given as MA deriving DE, EA deriving SY, and G deriving ATE, and D is deriving BMS. Okay, and the options are given below. So we have to, and the options are given below as like they have taken the closure out of these dependencies, they have taken the closure. Okay, so we have to see that which is the correct closure, like AD is the correct closure, or GM is the correct, G is the correct, or T is the correct. So out of all these dependencies, we have to identify which is the false closure. So let's verify the options one by one. Okay. Okay, so let's write the dependencies and then we can solve the problem. So let's see here. MA is deriving DE, and EA is deriving SY. Then G is deriving ATE, and D is deriving BMS. Okay, so these are the dependencies which are already given. Now let's find the attribute closure of AD out of all these dependencies. Okay, out of all the given dependencies. So the attribute closure of AD is, first of all, A and D will be as it is. So from A, are we going to derive anything? Is it possible to derive anything from A? No, it is not. So let's check for D. So from D we are able to derive BMS. Okay, so let's write it. B comma M S. We have derived this. Okay, and from A and M also we can derive D is already there, and E. So the new one will be E. A we can derive, S is already there, Y. Okay, and from G is not present. Okay, so we can't derive ATE. Means A is there but T we can't derive because G is nowhere there. Okay, in the relation. Now let's check the attribute. So A is there, yes. B is there, it is. D is there, E is there, M is there, S is there, and Y is there. Yes, so this is correct. So our option A is correct. But we want the false one. Okay, so that's why we will not tick the answer A. Now let's check for option B. Likewise, let's check the attribute closure of B. So the attribute closure of B, so for GM attribute closure we have to take. So it is G and M will already be there. So from G we are able to derive A, T, E, okay, ATE, and from M and A we are going to derive D and E. So E is already present, we will write D. And from D we can derive all the other attributes as well. So it is B, M is already present, S we will write. And from E and A we are able to derive SY. Okay, so S is already present, so we will derive Y. So you can see that all the attributes are covered. So let's check. A is there, B is there, D is also there, E is there, G is also there, M is there, S is there, T is there, and Y is also there. So likewise you can see that GM is also correct. The attribute closure of GM is also correct. Now let's verify the option C. So if we check the option C, so we have to check EG. Okay, EG we have to check. So the attribute closure of EG will be, E will already be there, G will already be there, and from G we are able to derive A, T, E. Okay, ATE we are able to derive, and from E and A we are we will be deriving S and Y. Okay, so E is already present. We will erase here this E. Okay, S and Y. S and Y. Okay, what else we can derive? From E and A we have derived S and Y. From G we have derived A, T, E. And anything else we can derive here? I guess no, we can't derive anything else other than this. So EG is the attribute closure of EG is also correct because A is present, E is present, G is present, S is present, T is present and Y is present. Okay, so attribute closure of EG is also correct. Now let's go for the option D and let's check the attribute closure of DT. Okay, so the attribute closure of DT is D will already be will be there. T will already we will write T also, and from D we are able to derive B, M, S. Okay, BMS we are able to derive, and anything else we can derive from T. Obviously we can't derive anything. B we cannot derive. M, S, no. So it is not possible. So here the real attribute closure of T contains D, T, B, M, S. But in the option what they say is that B is also present. Okay, so in the option they are saying that A will be present. Okay, B, D, M, S, T. So these are present but A is not present. So that's why our option D is false. So option D is the correct answer. Why? Because D is false. We want false one. So D is false because A is not in the attribute closure of DT. Okay, so let's move to question number 2. So consider three relational schema R1, R2, R3 containing 100, 200, 300 tuples respectively. So what is the number of tuples possible in natural join? So this is the natural join given. And in natural join, if we have to write it as natural join, so any in two table, okay, so here let's suppose we have two table. This is table 1, okay, and this is table 2. We have some attributes in table 1 and similarly we have attributes in table 2. So in table 1 let's suppose we have A, B, C, and in A2 we have D, E, F. So if we have to do natural join in between them, so in table 1 and table 2 one of the column or at least one of the column should be common. Then only we will be able to do natural join. And if in any means in two table no column is common, then we have to do like we have to do it cross product. Okay, we have to do cross product if the attributes are not common, and if attributes are common then we will do natural join in that. So similarly if we have to take for maximum tuple, so for maximum number of tuples of R1, R2, R3, they does not have any attributes in common. Okay, so we will take it as cross product. Okay, and we will do the multiplication. So you know the multiplication in the cross product. Okay, so what the explanation we can write for this one is for maximum number of tuples if R1, R2, R3 does not have any common attribute. So here they are asking us for maximum tuple. So obviously we will go for the worst case. So what can be the worst case of natural join? That no attribute is common. Okay, so that's why we are going for this case. So does not have any attribute, then there Okay, their natural joint will be same as cross product, will be same as cross product. Okay, it will be same as cross product, and the number of tuples and the number of tuples and the number of tuples in the result is equals to what will be the result? Cross product will be the result. So the tuple are given as 100 into 200 into 300. So we will do cross product. So this will be the multiplication and the answer will be 6 and 10. Yeah, so this will be the calculated answer. Okay, so the natural join here, the conclusion we can draw is, here they are asking us for maximum tuple, so we will go for the worst case where we will not have any attributes in common. So if in natural join we don't have any attributes in common, so we will do cross product of tuple, and we did cross product, so our answer came out to be this one. Okay, so the correct answer is this. Okay, let's move to next question.
Okay, so in a B tree of order 5, the following keys are inserted as follows. Okay, so we have given the order as 5. Let's write. Order is given as 5. Okay, and B tree is given. How many elements are present in the root of tree? So with this information, we can calculate maximum number of uh, so maximum we have 5 block pointers. Block pointers we have 5. Okay, and from this 4 keys per node we will keep. 4 keys per node we will keep. So let's take the 5 values. Okay, so 1 2 3 4. Okay, 1 2 3 4, and okay, four keys are there, so we will take 4 values. Okay, and 5 block pointers are there, so let's make 4 keys, 4 blocks. Let's make, so it will be 1 2 3. Okay, so 1 2 3 4, 4 blocks are there. We will keep the keys. It will be 1 4 6 and 9. Okay, 1 4 6 and 9. And now when 7 will come, okay, now here 7 will come, so it will split. Why? Because because the limit is only of 4, and if fifth one will there, so it will split. So how it will split? Like in root node, so 6 will be the middle node. That's why it will be root. And here it will be root. So we will put here 6, and again this will have 4 keys. So let's make the 4 blocks. 1 2 3 and here 4. So 1 2 3 4. 4 blocks we have, and the root is 6. So before that, now here the splitting will be of, like here one node will be form of 4 keys, and here other node will be form of 4 keys. Like this it will become. So 1 2 3. Okay, so this will also have 1 2 3 4, and this will also have 4. So 1 2 3 4, 4 keys, because the capacity is to store 4 keys. So 6 is the root, because it was the middle one, so we split it. And now here we can keep 1 and 4 here, and 7 and 9 we can keep like this. Okay, like this we can keep. Now what are the rest numbers? Like 7 we inserted, rest numbers are 11 13. Okay, so let's write here 11 and 13. We can keep this, but when 15 comes, again splitting will happen. Okay, why? Because it is exceeding the capacity. We have only four keys we can keep per node, but now fifth is coming. So again the splitting will happen. So here the splitting will happen as 11 is middle. Okay, so it will go here. So how the splitting will take place, I'll show. So again here it will be 6, and now here 11 will come. Okay, 11 will come, and the splitting will be taken as 3 nodes. So 1, 2 and 3. Okay, so like this it will split. So it will be 1, 2, 3. Means 1, 2, 3, 4 blocks are there. Again we will have here 4 blocks, 1, 2, 3, 4. Again in this also we will have 4 blocks, 1, 2, 3, 4. Okay, now here it will be 1, 4.
It will be 1, 4. Okay, so the rest we will have is 7, 9. Okay, here we will have 7, 9. And after the splitting, what we will get here? 13 and 15. 13 and 15 we will get. Okay, so when 12 will come, so it will accommodate here. Okay, 12 is done. When 3 will come, it will accommodate here. Okay, when 2 will come, it will accommodate here. And when 18 will come, it will accommodate here. Okay, so likewise there is no need to split again. So here in the root we will have two keys only, 6 and 11. So the question is asking how many elements are present in the root of the tree. So in the root of the tree, two elements are only present, which is 6 and 11. So the answer will be B. Two elements are present. Here you can see that two elements are present. Okay, let's move to next question. In this question, identify the minimal cover for the following FD set, functional dependency set, and the set is given as below. So we have to identify what is the minimal cover of all these FDs. So let's verify it one by one. Okay. So here A deriving BC. It is correct. We don't have to do anything about it. But let's check again, like C is deriving A. Okay, so here we will be writing the FDs, and after that we will cancel each other. Okay, so for this I am going to take next page, and in that I am going to explain you this problem properly, like how to minimize, how to do minimal cover from the FD set. Okay, so let's write the FD first. So it is A deriving BC, then C deriving A, BC deriving D, A, C, D deriving B, and BE deriving C, EC deriving FA, and CF is deriving BD, and D is deriving E. Okay, so let's check the FT one time. A is deriving BC, C is deriving A, BC is deriving D, ACD is deriving B, BE is deriving C, EC is deriving FA, CF is deriving BD, and D is deriving E. Yes, so these are the given functional dependencies. So we have to do what's the minimal in that. Okay, so we should not check for the extraneous attribute because we don't have here. It is the single attribute. So for this we will not check the one who has more than one attribute in left hand side. So for that we will check the extraneous attribute, means which is the extra attribute in this. So A don't have any extraneous attribute, so we will skip this. C also don't have any extraneous attribute, we will also skip this. But B has some extra attribute. So B is extra or C is extra, let's check that. So for that we have to check for if B is extra or C is extra. So to rectify that we have to take the attribute closure of B. And without this functional dependencies, we have to see that if we skip this, so can we derive, is it able to derive C from that? Let's see. So from B, if we see, then we can let's skip this. So with all these attributes, with all these functional dependencies, we can only derive B. We can't derive C. Okay. But if we take attribute closure of C, so C will be there. So from C we can derive A, and from A we can derive B. Okay, so C itself can derive B. So that's why we can say that here B is extra attribute. So we will cancel B. Okay, so likewise we will check for A, C, D. Okay, let's make the attribute closure of A. So attribute closure of A will derive A, B, C. Okay, this we can derive. So that's why C is also there. Can we derive D from A? Let's check that. So C, okay, C can derive D. Yes, C can derive D also. So that's why we can say that in attribute closure of A itself, we will derive B, C and D. So that's why here C and D are extra attributes. From C we can derive A, and yeah, C we can derive A. So that's why, but if we see the attribute closure of A, so C and D we can derive. So that's why C and D are considered as extra attribute. Okay, so let's check for B and E. So if we take attribute closure of B, we can derive only B. And if we take attribute closure of E, so we can derive E. Other than we can't derive in attribute closure E, we cannot derive B with E. So that's why they are not extra attributes. So we will keep them as it is. So it will be BE only. Now let's check for EC. So EC, so attribute closure of E will derive only E. We cannot derive C out of that. Okay, we cannot derive C. So now let's check the attribute closure of C. So from C we can derive A, from A we can derive B, C. Okay, we can derive this, and from okay, so now we have to check that from C can we derive E. Okay, we have to check that. So B, okay, so this we have, so BE, B and combinedly E we want. Okay, so is it possible? Okay, so from C we can derive D also. Okay, so this will be D. Here it will be D. And you can see that from D we can derive E. Okay, so C attribute has E also. So C can derive E also. So that's why E is here extra attribute. So we will cancel E in this. Okay, now let's go for C and F. Like attribute closure of C, can we derive F in that? I guess no. From here only we can see that we cannot derive F. Okay, so let's check. So attribute closure of C. Okay, so here we have taken already the C closure, and here from you can see that from C we can derive F in this closure. This closure we can derive F also. So that's why here F is the extra attribute. So we will cancel this. And from D can we derive E directly? So from D we can derive, okay, so this we will not check because D don't have any extra attribute. So let's write the optimized one. So I hope you understand how to eliminate the extra attribute in this. Simply we have to take the attribute closure and we have to check that if the other attribute is present in that. So if it is present, it is extra attribute, otherwise it is not. And for single one, we don't have to check. Okay, so what will be the attributes we have now? A is deriving BC is same. C is deriving A. Okay, so we will write it as single. So that's why now the step is to rectify the redundant attribute. Redundancy we have to minimize. Okay, so that's why we will do A is deriving B. A is also deriving C. Like this we will write. Then C is deriving D. A is deriving B. Okay, so this is redundant. So that's why we will not write it again. Let's erase that. Okay, now BE is deriving C. C is deriving F and C is deriving A. C is deriving B, and C is deriving D, and D is deriving E. Okay, D is deriving E. So now what we can see that here C and B is already created. How? Like if you can see uh, here, if you can see that is this one, C is deriving A and A is deriving B, so we can say that C is deriving B. So from these two we are able to derive this, so that's why this is reductant. That's why this is not what we want. Okay, so let's check similarly what are the other reductant functional dependencies which is hard to derive. So from A, can we derive B? If we don't take this, from attribute closure of A, can we derive B? Okay, so from A we can derive C, C we can derive D, D we can derive E, but we cannot derive B. So that's why this is not reductant. From A, attribute closure of A, can we derive C directly? We can derive B, but we cannot derive C. Okay, so that's why this is also not reductant. C also, if we take attribute closure of C, so we can derive F, A, but from that we cannot derive D. Okay, so that's why this is also not the reductant one. And BE, this is the unique one that we can derive C. So C from F, if we take the attribute closure of C, so it is not possible that we can derive F. So that's why this is also reductant. From C and A, okay, we can derive C and D, but not A. So that's why here this is also not reductant. And this is cancelled. I already told you the reason, like this is why this is reductant. And from C and D, we can derive A, F. Okay, so these two are similar, so that's why we will erase this. This is also a reductant. Okay, and from D and E, from D, attribute closure of D, if we take and we consider all these FDs, can we able to derive E? So no, it is not possible, so that's why this is also unique. Okay, so these are all unique ones. So let's write this in combined form. So A will be able to derive BC. Okay, so this and this is done. C will be able to derive DFA. Okay, so from C we will be able to derive DA. Okay, ADF. ADF. So this is done, this is done, this is done. Okay, this is already cancelled. And from BE, we are deriving C. And from D, we will be deriving E. So this is the minimal cover we did for the functional dependencies. So that's why, which is the correct answer for this? Let's see with the option. So if you can see that A is able to derive BC, so this is, and then C is able to derive ADF, so this is also correct, ADF. D is able to derive DE and BE is able to derive C. Okay, so that's why A is the correct answer for this question. Rest you can see that here A is not able to derive B, so that's why this is incorrect. Here this is correct, but here E is also it is deriving, which is incorrect. Here BC it is properly deriving, C also it is properly deriving, but E is not deriving anything. Okay, but here in this they are showing that E is deriving D. No, it's opposite. D is deriving E. Okay, so that's why this is also incorrect. So the only correct option here is A. Okay, let's move to the next question now. Okay, so the question is Amy and Bob are working on a project, vehicle rent system. They have a file consisting of 1000 records, having block size 1024 bytes, record size 100 bytes, search key is given as 9 bytes, pointer is given as 7 bytes. They want to implement single level indexing. So here we will they are working on single level indexing. Okay. Bob suggests to implement first level index using dense index. Okay. However, Emmy suggested to implement sparse index. So how many blocks are saved by Emmy considering only first level index? Okay. So let's write the information which is given. So the information which is given as file size is given as 1000. Okay, it is 1000 or 10,000. Okay, so the file size is given as 10,000. It is given as 10,000. Okay, and the block size is given as 1024. Okay, now they are saying number of entries in first level of dense index equals to number of record in file. Okay, number of entries in first level of dense indexing equals to number of records in file. So it will be number of index equals to 10,000 divided by block factor of index block. So we read the question, and from that we decoded some information like the file size, block size, and what the number of entries will be equals to. It will be equal to the number of records in file. Okay, so after that, so number of index, we will have 10,000 divided by block factor of index block. Okay, so what it will be? So now if we have to calculate block factor of index, so it will be this size divided by number of indexes. Okay, so let's do it. So therefore, let's take the other page. Okay, so now it will be block factor of index block will be 1024 divided by 9 plus 7. So if we do the calculation, then it will be 64. Okay, it will be 64. And 9 plus 7 we did because we have given the search key as 9 bytes and pointer as 7 bytes. So that's why we have done here 9 plus 7. And it will be divided by 1024. So the answer comes out to be 64. Okay, now let's calculate number of index first level blocks. First level blocks, which is, so the ceiling we will take So ceiling we will take 10,000 divided by 64. So now it will come out to be 157 blocks. Okay, it comes out to be 157 blocks. Now let's calculate the number of entries in sparse index. So number of entries in spare index, it will be equals to number of blocks in file. Okay, it will be equal to number of blocks in file. Okay, so now number of blocks in file, which is equals to 10,000 divided by block factor of file. Okay, block factor in file. It will be block factor. Now let's calculate what will be the block factor. So the block factor will be 1024 by 100. Okay, now we will take the here we will not take the ceiling value because integers, how block factor will be in integer. Okay, so that's why we will not take the ceiling value. Instead we will take this like 1024. So the value will comes out to be 10. Okay, 10 records per block. It will be 10 records per blocks. Okay, now let's calculate the number of blocks. So it will be 10,000 divided by 10, so it will be 1000 blocks. It will be 1000 blocks. And now number of index blocks equals to 10,000 divided by 64. So now it will be 16. Okay, now it will be 16. Then the number of blocks saved by ME is 157 minus 16, so it will be 141. Okay, so first we took the spare index, like how many the blocks we will get. So the answer we got is 157. After that we went, so we first did the index block. Okay, we first calculate the values of index block, like the number of index in the first level block. So it came out to be 157 blocks. After that we take the spare indexing which ME suggested. So in this question also you can say that Bob suggested to implement first level indexing using dense index. However, ME suggested to implement sparse index. Okay, so with first level indexing we got 157 blocks, and with the sparse indexing we got 16. So that's why so the number of blocks saved by ME. So obviously we will do 157 minus 16. We will do the subtraction, and the answer will comes out to be 141. So I hope this question is clear. Let's move to next question. Okay, so which of the following statement are not true? So A is lossless dependency preserving decomposition into NF3 is always possible. So lossless and dependency preserving decomposition into NF3 is always possible. Option A is saying that, and we have to see that which is not true, means which is false. So which is the false statement that we have to see? So this is the correct statement, like in 3NF. It is always possible that lossless and dependency preserving decomposition will happen. So option A is true, but we want false. So let's look at the option B. In option B, it is saying that a relation in 3NF may always satisfy BCNF. Okay, a relation in 3NF may always satisfy BCNF. Yes, this is also possible. Now let's see for C option. A relation in which every key has only one attribute is in BCNF. Okay, so this is not possible because it may have transitive dependency. Okay, so that's why C is false. So it is correct answer. And option D says, like a relation in which every attribute is prime attribute is in BCNF. So it is also false because it may in 3NF but it may not be in BCNF. Prime attribute for this, it may be in 3NF but it may not be possible that it is in BCNF. So that's why option D is also incorrect. So let's write the reasoning for this, option C and D. So C reasoning is it may have transitive dependency. It may have transitive dependency. And the D reasoning is it is in 3NF but may not be in BCNF. Okay, but may or may not be in BCNF. So this is the reasoning for C and D. And so the correct answer is C and D. I hope this is clear. Let's move to the next question. So here they are saying, consider a relation and the attributes given as A, B, C, D, E, F, G, H. How many super keys will be there? Okay, how many super keys will be there in relation R if candidate key for relation R? So this is the relation R is given. Let's write R relation is given. The attributes given as A, B, C, D, E, F, G, H. These are the attributes given. How many super key will be there in relation R if the candidate key for relation R? So CK is also given. CK is given as A, then BC, then C, D, E, okay, and then E and F. These are the candidate key which are given. And they are asking us to calculate super key. So if the candidate keys are given, so we have the formula, right? We have the direct formula, so we can put that in the values. Like how many attributes we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so how many how many attributes are there in the candidate key? Let's count that. 1, 2, 3, 4, 5, 6. Okay, these are the attributes. Okay, now let's calculate the super keys by using the formula. So first it will be 2 to the power 7 plus 2 to the power 6 plus 2 to the power 5, okay, plus 2 to the power 6 minus 2 to the power 3, okay, it will be 2 to the power 5 itself, minus 2 to the power 5 minus 2 to the power 4 minus 2 to the power 5 minus 2 to the power 4. Okay, so first of all it was 2 to the power 7, then 6, then 5, then again 6, then minus 2 to the power 5, minus 2 to the power 4, then again minus 2 to the power 5, minus 2 to the power 4, again it will be minus 2 to the power 4, then minus 2 to the power 4 plus 2 to the power 3, plus again it will be 2 to the power 3 and 2 to the power 3 minus 2 to the power 2. So likewise we simply have put this in the formula. Okay, so here if we do the calculation, it will be 188. So this is the simple calculation we did and the answer is A. But let's see the method, like let's see the formula, like how we calculated 2 to the power 7, 2 to the power 6, 2 to the power 5, again 2 to the power 6, how all these values came. Let's go into that. Okay. So For this I have to add a slide. Okay, now the given attributes are given as 8. You can see this in question. Given attributes are 8. 1, 2, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so here they are. Okay, wait, let's check once again. Yes, the given attributes given us 8. Here we can count it as 1, 2, 3, 4, 5, 6, 7, 8. So we have written the given attributes as 8. Now, what we will do, we have formula for this. If we have to calculate super key, so we have the formulas. Like, let's just take the for example, let's take W, X, Y, Z. Okay, we have taken 1, 2, 3, 4. Here we have taken the number 4, and let's see how the formula works for this if we have to calculate super key. So it will be number of super keys. So we will do, okay, OR operation because we want super keys. So this will be, okay, so likewise, so what will be the formula? So number of W's plus number of X plus number of Y plus number of Z. This we will do. Okay, so like this we did, and after that what we will do, we will subtract the intersection of these two. Like first we will take Wx, then we will take Wy, then we will take Wz, then we will consider xy, xz, then we will consider yz. Okay, so like this combinations, intersection combination we will subtract. So for now we will take 2 intersection. Okay, so let's see this. So first we will take number of W and X intersection we will take, then minus number of W and Y intersection we will take, then again we will do subtraction number of W and Z intersection. Okay, so X taken, Y taken, and Z is left. Okay, so this we will take. After that what we will do, we will again subtract number of X intersection with Y and number of X intersection with Z. Okay, this we will do, and the left one for the 2 pairs is number of Y intersection Z. Okay, now we have taken 2 pairs. Now the time is to take 3 pairs like W, X, Y. All the intersections we will take one by one for this. So now subtraction of number of W intersection X intersection Y, then number of W intersection X intersection Y. Okay, so here we have taken Y, so now we will take Z intersection. Like this we will do. Now again what is left? Number of X intersection Y intersection and Z intersection. Okay, X intersection, Y intersection, Z intersection. Likewise we will do. And again Y intersection, Z intersection. Okay, so this is only possible, and after that we will do all the attributes intersection. So we will subtract all the attributes intersection at the end of all the combinations we tried. After that we will do this. So number of intersection we will subtract W, X, Y and Z, like this we will do. So this is how the formula will work. So in our case, W value we have A, okay, X value we have BC, Y we have, okay, Y we have C, D, E we have, and for Z we have E and F. E and F. So what we will take? We will take 2 to the power. Now this will get subtracted by 1. Okay, because here the candidate key is A. So 8 minus 1 is 7. So that's why here 2 to the power 7 will be there, plus Now x will be, x has 2 values, so we will subtract 2 from 8, so that's why it will be 2 to the power 6. After that, y value we have 3, so 3 we will subtract, so that's why it will become 2 to the power 5 plus, okay, let me change the color so that you will get, okay, let me write this in different color. Okay, so it will be 2 to the power 7, okay, because we have one key. And for this we have two keys, so we will subtract 8 minus 2, it will be 2 to the power 6. And here we have 3, so we will subtract in y, we will write it as 2 to the power 5, okay. And for z we will now write it as 2 to the power 6 itself, okay. After that, what we have to do, intersection. So A, B, C. Still we have nothing in intersection, so we will consider as A, B, C only. So 8 minus 3, it will be 5. Okay. It will be 2 to the power 5. And after that, W and Y. If we do W and Y, so still we don't have anything in common. And we have 4 attributes. So 8 minus 4 will be 4. So it will be 2 to the power 4. After that, W and Z we will take. So still we don't have anything in common. So it will be 2 to the power 5. Then X and Y, if we take X and Y, so we have C as common. So that's why we will take 1, 2, 3, 4. So that's why it will be 2 to the power 4. Double attributes we don't have to consider it. Like we will not consider it. Like X and Y we have C in common. So we will consider C only one time. So likewise 1, 2, 3, 4. We have 4 and 8 minus 4 is 4. So that's why here we wrote 2 to the power 4. And X and Z, if we take X and Z, so we don't have anything in common. So that's why it will be 4 to the power 4. Okay. And then Y and Z, if we take Y and Z, so E is common. So we will consider it as one time only. So 1, 2, 3, 4. So that's why it will be 4 to the power 4. Then WXY, if we take WXY, all this, so we have C in common. So that's why 1, 2, okay, 1, 2, 3, 4, 5. So 5 minus 8 is 3. So that's why it will be 2 to the power 3. Now we will do WXZ. So we don't have anything in common. So that's why it will be 1, 2, 3, 4, 5. So again it will be 2 to the power 3. Okay. After that, XYZ. XYZ if we take. So here what we have common, we have CES in common. So that's why we'll take it as 1. We will consider it as 1 only. So 1, 2, 3, 4, 5. So 5 minus 8 is 3. So it will be 2 to the power 3. And now the whole we have to take intersection. So it will be 1, 2, 3, 4, 5, 6. Okay, 6. And 8 minus 6 is 2 to the power 2. So now what we got? Let's write 2 to the power 7 plus 2 to the power 6 plus 2 to the power 5 plus 2 to the power 6. Now minus 2 to the power 5. Okay, first minus is 2 to the power 5 minus 2 to the power 4 minus 2 to the power 5 minus 2 to the power 4 minus 2 to the power 4. Again it will be 2 to the power 4. Okay, so one thing which I did wrong here, that it will be when you will make the combination of 2. So it will be minus, but when you will make the combination of 3, then it will be plus. So here it will be plus. In 3 combination, here it will be plus. And again, if you will do whole combination, we will consider it as minus. So how it will work? First we will do with 1 combination, it will be 1. With 2 combination, we will subtract. With 3 combination, we will add. And with 4 combination, again we will subtract. So it will be plus minus plus minus. Like this it will follow. So according to that, it will be plus 2 to the power 3 plus, again 2 to the power 3 plus 2 to the power 3. So it is 3 times. No, it is 4 times. Okay. Then subtracting the end, this one is 2 to the power 2. So if we calculate all this calculation, so the answer comes out to be 188. So that's why what is our correct answer? It is 188. I hope you understand this question. Let's move to next question. Okay. So a relation R is A, B, C, D, E. Okay, A, B, C, D, F, G is given. So these are the attributes we have given. And the functional dependencies is given and we have to calculate the candidate key. We have to calculate the candidate key. Okay. So now so the attributes we have given is this. Functional dependencies also given. We have to calculate candidate key. So for candidate key, what is required? Like if we will take attribute closure, and in the attribute closure, if all the attributes given in the relation we are able to derive that, so it will be our candidate key. So first of all, let's check it by the option method, and then I have one shortcut method to solve this question. Such type of questions we will also discuss that. So let's take the attribute closure of A. So A we have, and from A we can derive B. From B we can derive F. So can we derive anything from F? Can we derive anything from A and B? Let's check that. No, we cannot derive. So that's why A is not the answer. Okay, A is not candidate key. Now let's check for AD. So it will be A, D, and from A we are able to derive B. From AD we can derive C. From B we can derive F. From A we can derive G. From D we can derive. So you can check that AD is able to derive every attributes in the relation R. That's why we can say that AD is the candidate key. Okay, now let's check for AC. AC attribute if we take, so it will be A, C, and from A we are able to derive B. Okay, from B we are able to derive F. From A we are able to derive G. From, okay, anything else can be derived? Okay, we cannot derive D in this. So that's why AC is not the candidate key. Now let's check for D, attribute closure of D. So D and B, can we derive? Yeah, from B we can derive F. Anything else can we derive apart from this? No, we cannot derive. So that's why D is also not candidate key. D is also not our candidate key. Okay. So this is the option method. So from the options we can derive attribute closure and we can check that in which option all the attributes are present. Likewise we can do. Now let's move to other method, which is the shortcut method. Let's discuss that. Okay, so for the shortcut method we have to make one horizontal table. And then we have to write each attribute which is given in question. So R has A, B, C, D, F, and G. This is given. Now after that, whatever will be the deriving part, we will make arrow to it. Like A is deriving B, so we will make arrow on B. Then AB is deriving C. Sorry, A and T are deriving C. So in deriving C, so C will have arrow. Then B is deriving F. So F will have arrow. And A is deriving G. Okay, so A is deriving G, so G will have arrow. D is deriving B. Okay, so D is deriving B, so B will have arrow. So now after this, okay, so let's check the attributes which don't have arrow. So A don't have arrow, so that's why we'll take A. B has arrow, so we will not consider B. C also has arrow, so we will not consider C. D don't have arrow, so we will consider D. F has arrow, so we will not consider F, and G has arrow, so we will also not consider G. So after that, we will take the attribute closure of AD, and we will check that whether we are getting all the attributes in relation R or not. So let's check that. From A we can derive A and D. Okay, from A we can derive B. From AD we can derive C. From B we can derive F. From A we can derive G, and from D we can derive B. So yes, the attribute closure of AD we are able to derive everything, so it is the candidate key. And let's suppose AD is not able to derive all the attributes. So what we will consider, like AD is mandatory, it will be key, but now we have to make combination. Like we will make combination of ADB, ADC, and we will take the attribute closure. Okay, if in first go, if it is able to derive everything, then for sure it is candidate key, but in first go itself it is not deriving every attribute. So from that we will consider, we will make the conclusion that AD is mandatory to be present in key. Now what, to derive all the attributes we have to take combination with other attributes. So like that we will do. Okay, so from this method we learned that how to calculate candidate key. So our option B is correct. Let's move to next question. So this is the question. So the option 1 is A is given as the intersection. Okay, so this is the intersection operator can be derived using minus, which is basic binary operator in the relational algebra. So now here in this question we have to mark the correct options. Okay, so the option A is saying that intersection operator will have minus, and minus is basic binary operator. So let's check. Okay, let's check. So now if we consider the example of, let's suppose, R intersection S. So how we can write this as R minus of R minus S. We can write this like R minus S we did, and with this we subtracted from the original R. So this is also intersection. Okay, or we can also do this as S minus bracket S minus R. Okay, so S minus R we will do, and we will subtract the whole from S. So this is how we can write the intersection operator. So it is correct, option A is correct, that intersection operator can be derived using minus, which is basic binary operator in relational algebra. So that's why this is correct answer. This is correct answer. Okay, now let's verify option B. So the join, this is the join operator, can be derived by using, so this is cross in the sense cross product, this is a selection operator, and this is projection operator. So all the operators are given us. Okay, so this is cross product, this is this is selection, and this is projection operator. So can you say that join operator requires all these three? Let's check that. So this is the reasoning for A. Let's do the reasoning for B. Now let's suppose we consider this relation. We have two attributes AB, and again we have the other relation S which has attributes BC. And now we have to do the natural join. So how we will do the natural join? So let's suppose we will do join of R and S. So it will be, first we will do cross product of R and S, and if we have to do the natural join, so in the selection, and we will do the selection, and for cross product we will apply the condition like R of B should be equal to S of B. So this is what natural join, because we have two attributes in common. So whatever the two attributes we have common, we will do that. After that we will apply the selection one. Okay, selection operator we will apply. and after that we will do the projection of ABC. Okay, we will do the projection of ABC. So from this if we have to do the join, so we require cross product, selection and projection. So that's why option B is also correct. Option B says to perform join operator, it can be derived by from cross product, selection and projection. So here in our explanation also you can see that we have used all the three operators. Now let's see question number C. Okay, so the division operator can be derived by using cross, selection, projection operator. So let's see, do we really require all these three operators? Okay, let's see the option C. So let's suppose we have to take the projection of AB in relation R, which is divided by projection of B in relation S. So how we will do this? First of all, we will take the cross product. Okay, so we will take it as projection A in relation R, cross product of, okay, so here we want space. So basically how we will do this, let's see. So this will be the projection of A R, okay, minus projection of A bracket projection of A R cross of projection B S, okay, minus of projection AB we will take on relation R and the whole. So this will be the division operator if we do. So in the division operator we required projection and cross product. Projection and cross product. There is, here you can see that we didn't need any selection operator. We didn't use here selection operator. We just use cross product and projection. So clearly from this option C is false. Option C is false. Okay. And what you can see here from that, so clearly from C option we can say that option D is true, because what it says, the division operator can be derived by using cross product, projection and minus operator, which is true. See, you can see in this example we use three operators, which is projection, minus and cross product. So option D is correct. Okay, let's move to next question. So consider a relation R with instance R is given is decomposed into sub-relation. So this R is decomposed now in sub-relation like R1, R2 up to Rn, sub-relation. Which of the following statement can never be true? So we have to consider, we have to mark like which of the following can never be true. Means which is false. Basically we have to say that which is false one, we have to detect. False we have to say. Okay, so let's check. Okay, so here the relation is given as R and they have done the decomposition of this R into, it will be R1, R2, R3, R4 and so on up to Rn. Okay, like this they have decomposed. Now what they have said that if they have taken natural join of all the decomposed relation, so now there can be two cases possible. Okay, so let's discuss the case 1. Case 1 will be like if we take this sub-relations joined. Okay, if we take the natural joint of all this relation R1, R2, R3 up to Rn. So it will be equals to R. It will be equals to R. Okay, so in this case we will call it as lossless joint decomposition. Lossless joint decomposition. Okay, so this is lossless joint decomposition, we can say that. Or the second possible cases, The second possible case is if we take natural join, okay, of R2, R1, R2, R3 and so on up to Rn. So it is possible that if the selection is not possible, so because of this we can be able to derive many rows, okay, many rows many tuples can be derived, okay. So that's why this can be greater than R, okay. So this can be greater than R because of false selection. It is possible that we can have extraneous attributes we can have, so extraneous values we can have. So this is clearly possible. So in this case it will not be lossless join decomposition, okay. So these are the two cases possible. So here an option A is possible because of extraneous attributes if we have, so this is also possible. So option A is correct. Option C, if we see that if it is equals to R, this is also possible if the selection is possible, the selection is properly done on natural join. So we will get R, we can get R completely, okay. And D is also correct because if we get R, so it is clearly it is called as lossless join decomposition. But subset is not possible. We can have extra attribute, extra rows, but we can't have less, okay. So clearly from this option B is not possible because we cannot have, because all the join cannot be subset of R. So this is false. So option B is false. So that's why the correct option is option B. Option B is correct. Okay, let's move to next question. A relational database, there are three relations. Okay, so customer is given as C name, shop is given as S name, and buys we have two attributes, C name and S name. So customer and shop. So in buys we can have, means if a user buys, so definitely we will have like customer name, like who buy the product and from which shop. So from in buys we have all the two attributes. Then the relational algebra expression, which is C minus projection of C name into cross product of C into S minus B. So returns the name of. So the option A is given as customer who buys from at least two shops. B is customer who buys from all shops, and C is customer who buys from at least one shop, and D is customer who do not buy anything at all. So clearly in the from this expression, what you can say that from this expression we can say that it is the implementation of division in relational algebra, okay. So how it will be, let's write. It is implementation of division in the relational algebra so it will be division, which is projection of AB in relation R divided by projection of B S. So this is what the implementation we can see. Okay, so the given so this is clear. Now let's write what is the given expression. Okay, so what the relation is given? C minus projection of C name, okay, into C cross S minus B. So this is the expression which is given to us. This is the expression which is given. Now let's see that what it says. So let's see this expression. So it is C name of customer, okay, into S name of ship, S name of shops, S name of shops. Okay, so from this we will get every pair of customer and shop name. So from this we will get every pairs of C name and S name. C name and S name. So it is divided by B, and what B has? C name and S name of buys. So we will divide this, we will minus this from every pair of C name and S name. After that, what we will do? We will do the projection of C name. So now from this information, what we have? We have C name. Okay, and we will subtract this from C, which is C names of all customers. We will subtract this from all C names of customers, and the attributes we have C name. Okay, so what we will have? So from this we can conclude that C name who buys from all shops we will get. So from this what we will get? C names who buys from all shops. Okay, now let's verify the options. So option A is customer who buys from at least 2 shops. No, it is not correct, because what we will get from, like, who will buy from all shops. So B is correct because it is saying that customer who buys from all the shops. C is saying customer who buy from at least one shop. This is false. D is saying customer who do not buy anything at all. So this is also not possible. So option B is correct. So this this relational algebra expression will written customer who buy from all the shops. Okay, let's move to next question. So this question we have, like, considered the following relation A, B and C. So A we have given as SID, S name and age. B is given as SID, S name, age. C is given as SID, phone and area. How many tuples does the result of the following relational algebra expression contain? Assume that the schema of A union B is same as that of A dot and A union B joint is given as A set should be greater than 30, and the union is given as, okay, so this is not union, this is OR, which is should be CSD 20. And after that, if we do this, then we have to do the join of C. Okay, so let's break this one by one. Okay, so let's see what we will get from A union B. Okay, let's see that first. So if you will see A union B, so in A union B, what are the tuples we will get? What are the attributes we will get, which is CID, C name and age? It is same. what are the attributes we will get? The attributes we will get are 12, 15, 19, 12, 15, 19 and 99. These are, yes, this we will get. Union we have to take, so 12 also we will get, 15 we will write one time, 19 we will write, and 9 we will write. So now Arun we will get, after that Shreya we will get, and in 19 it will be Hari, and in 99 it will be Rohit, and their respective age will be 60, 24, 40 and 11. So this is A union B we will get. Okay, now so union is so you have to keep remember for union operator, one note is there for union operator. Union operator, one note is there that it is a set operator. It is a set operator and duplicate will not be included by default. Okay, it not be included by default. So union operator. In this also you can see that you can see 15 and 50. We just wrote this for one time only. We didn't write for two times. So by default it is, we have to write it one time. We will not take it as duplicate value, like 15 and 15 we will not write. We will write 15 for only one time. So this is the union operator note. Now let's check. Let's do. So okay, now we have to decode these one. So let's do it. Okay, so we have to, okay, so this we have to do. A dot sit is greater than 30. Okay, and we have to do union of AB, and then we have to do cross of C, like this we have to do. Okay, so first of all what we will do, we will multiply each row of AID and we will check that if it is greater than 30, and which will be the union of AB with each row of C. Okay, like this we will do. So from this what we will get, first of all let's discuss the, okay, from C if we do, so A union B and the cross product of C. Okay, clearly you can see that we have to do A union B into C. So A union B, we already know the attributes in A union B is SID, SID, S name and age. And what will be the new, we have to do cross product in C. So what will be the new attributes added, like CID, phone and area. Okay, so let's write the area. So let's write the attribute as per to this. So attributes we will have SID, S name, age. So for now we are only going to do this one. Okay, we are going to consider all of this. Okay, so let's write this. After that C dot SID, then phone, and then area. We here we wrote C dot SID because we should not have the confusion, because this CID is the union of A union B and this is the C CID. Okay, now let's write the attributes in this. So we will get here we will get is 99, 99 and 99. So if you do the union and cross product, so we have to do the union and cross product. Okay, so 12 and 10. Now 12 and 10, but the condition is we will only select the row if ACID is greater than 30. If ACID is greater than 30, then we will consider the tuple. Okay, so let's see. So ACID, so here 10 and 12. So ACID is not greater, so we will not take this. Then 12 and 25. So definitely ACID is not greater, so we will not consider this. Then 99 and 12. So ACID is not greater, so that's why we are not taking this also. Now 15 also we will do similarly. So similarly 12, 15 and 19. They are not greater than 30. So that's why we will not consider them. So what we will consider only this one, 99, because it is greater than 30. Okay, so that's why we will do the cross, that's why we will do the join, and we will do the cross product to all these tuples. Like 99 will be matched with 10, it will be matched with 25, and it will be matched with 99. Why here 99 only we are taking? Because in the question itself they are saying that it should be greater than 30. So only value we have greater than 30, it is 99. So that's why we will take this and we will join with all the values of C. So what the tuples we will get is 99, 99, 99. Okay, and the name will be Rohit in all the rows. The age will be 11. Okay, now SID will be 10, 25 and 99. And the phone number, it is this. Area will be 03, 04, 05. Okay, so these are the tuples. These are the table we got. Now what we have to perform? Cross product of C. Okay, so now what we will do? So after this we have to do A union B cross product of C dot SID should be smaller than 20, and we will do the cross product of C. Now what we have to do, like it will be also written as, this is very similar to the previous one. Now we have to check CID should be small than 20. We will do the union and the cross product with 20. Okay, so what will be our tuples? So CID should be smaller than 20. So 10 is smaller than 20, 20, 20. Okay, 5 is not smaller. This CID is not smaller than 20, so we will not consider this. 99 is also not smaller than 20, so we will also not consider this. So this 10 we have to do cross product with 12, 15, 19 and 99. Okay, we have to do cross product with every of this, and CID will be 10. So from this we will get the table as, okay, so CID we will get, S name we will get, age we will get, then C dot CID we will get, phone we will get, and the area we will get. So now the CID will be, okay, so we want 20, smaller than 20. So we have only 10. So we will write as 1, 2, 3, 4. And as we are going to do cross product with union, so we have 4 tuples. 1, 2, 3, 4. So we will write all the 4 tuples. So it will be 12, 15, 19 and 99. The name will be here Arun, Shreya, Hari and Rohit. The age will be 60, 24, 40 and 11. Okay, and the rest of the information we will write. This is actually 3. Yes. So this is what the table we will get. Okay, so these are the tables we will get. Now what we have to do in the question, what they have said, like we have to do the union of this, of all these two tables. So this is table 2 and here is table 1, and in the question they have said to do union of two tables. Okay, so first you can clearly see that we broke the question, like we broke the question in two tables. So this is one table and this is two table, and after that what we are going to take the union of two tables, which is clearly said in the question. See, you can see this, we have to take the union. So for union, our, so in both the tables attributes are same. Okay, attributes are same. Now we have to write the row one by one, but we have to eliminate the duplicates while writing the union. Okay, let's make the final table. Okay, let's make the final table. So this is table 1, this is table 2, and now the union we will take. Okay, so the union we will take it as, we will have, we have to write all the tuple, all the attributes, SID, SName, age, and C.ID, C.SID, phone, and area. Okay, now let's write it one by one. So first we will take 12, Arun, age will be 60, CID will be 10, rest information we have to copy from the table itself. Then second CID will be 15, it will be Shreya. You can see the two tables and you can simply write this. 24 the union. Only the thing you have to be careful in union, you don't have to write the duplicate rows. Two rows you have to consider it as one and write. Eliminate the duplicates in union. It will be Hari, 10, this, and 3. Then it will be 99, Rohit. It will be 11, 10, and 3. Okay, again it will be 99, 99. Okay, here it will be Rohit, Rohit. It will be 11, 11, 10, 25. Okay, 10, 25, and 99. It is 10, here should be 25. Okay, so here it will be 25 and here it will be 99, and then it will be 2 1 0 0 2 3 like this, 4, and yeah, so this 2 we will have. So what is this happening? Oh, so you can clearly see that one by one we will consider a table from the 1 and 2 table, and we will write this likewise. Okay, so how many tuples we will get here in this? They have asked us the number of tuples. So we will get 1, 2, 3, 4, 5, 6. So our answer will be 6 tuples we will get. Okay, let's move to next question. Consider a relation R having 7 attributes. So in question itself it is given that there are 7 attributes, field of R contains only atomic values. So R has only atomic values and the number of attributes we have are 7. So functional dependencies are already also given. How many candidate key does the relation R have? Candidate key we have to calculate here in this. So functional dependencies is given. We have to calculate number of candidate key. Okay. So to calculate candidate key, let's take the attribute closure one by one. Let's take the attribute closure of CD. It will be C, D, and from CD we will be able to derive G. Okay, and from G we will derive D, which is already derived. Can we derive anything from C, D, and G? Let's check. So no, we cannot derive anything other than this. So that's why CD is not the candidate key. Now let's take the attribute closure of A. So if we take the attribute closure of A, so it will be A, B, C, and from B we will derive F. Okay, from F we will derive E and G, and from G we are able to derive D. So let's see all the 7 attributes are derived or not. So 1, 2, 3, 4, 5, 6, 7. Yes, all the 7 attributes are derived. So we can say that A is CK, which is candidate key. Now let's take the attribute closure of B. So from B we will derive B, we will derive C, F. Okay, F we can derive E and G. G we can derive D. Can we derive anything else? 1, 2, 3, 4, 5, 6. Okay, we want 1, which is A. So can we derive A? Let's check. So yes, E can derive A. E can derive A. So okay, so this is also candidate key. Okay. So from this we can say that B is also CK. Yes, from this we can say that B is also CK. Okay, now let's check for C. So C is deriving C itself. Can we derive anything from C? No, we cannot derive. So that's why C is not CK. Let's check for D. So if we take the attribute closure of D, so we'll have D. And can we take anything from D? No, we cannot derive. So that's why D is also not candidate key. Now let's take the attribute closure of E. So E we can derive. From E we can derive A. From A we can derive B, C. From B we can derive C, F. From F we can derive E, G. So okay, let's check all the 7 attributes are derived or not. So it will be 1, 2, 3, 4, 5, 6. Okay, one attribute is left. Let's check which is left. Okay, D is left. So G will derive D. So yes, it is completed. So E is also CK. So now we got 3 attributes. The one more attribute left is 2 attributes left to check. They are F and G. Okay, let's check them. Okay, so if we take attribute closure of F, so what we will get F, E, G, G we can derive D, from E we can derive A, from A we can derive B, C. Okay, so 1, 2, 3, 4, 5, 6, 7, yes. So here F is also CK. Now let's see the attribute closure of G. So from G we can derive G, D. From D can we derive anything? No, we cannot. So that's why G is not CK. So now if we will do, now there is no chance to check for AB or such combinations. Why? Because they will be super key, not candidate key. Super key, there is, means super key will be the combination of candidate key, we can form super key. But in candidate key it should be minimal. So the minimal key which we will get is considered as super key. So that's why the candidate key we got as A, B, E and F. So these are the 4 candidates key we got from this functional dependency. So the question is, how many candidate key does the relation R have? So the answer will be 4. 4 candidate keys. Okay. Let's move to next question. Which of the following statements are not true? Option A. If relation R has n distinct tuples and relation S has m distinct tuples, then cardinality of R intersection S lies between 0 to minimum of m n. So in the question we have asked for the false statement. So this is actually true, that if we have relation R has n distinct tuples and relational R has m distinct tuples, then the cardinality of R intersection S lies between 0 to minimum of m and n. So this is correct statement. Now let's check for B. Relational algebra and SQL have same expressive power. So this is false, because if we will do sum and average etc., so not possible over relational algebra. Okay, so the power are, so they don't have similar power. Okay, they don't have similar power, so this is false. And what C is saying, minimal cover or canonical cover is always unique for FD set. So this is also false, because there can be more than one minimal cover for some FD set. Okay, it depends on us. So this is also false. And unique not null is equivalent to primary key. So actually they are different. Nulls are different. So unique not null key is not equivalent to primary key. So this is also the false statement. So option D is also false. So from this, false are, so our answer is B, C and D. Okay, let's move to next question. Consider the following relation. The attributes given as A, B, C, D, E, F and the functional dependencies are also given. What is the highest normal form of the given relation? That we have to see. So for that, for this we have to calculate the candidate key. Okay. And here, since every attribute is atomic, therefore there is no okay. So here here the attributes are atomic. So that's why definitely it will be in first normal form. Okay. Now let's calculate the candidate key. So let's calculate the attribute closure of A. So from A we will get A, B, C, D, E, F. Okay, all the attributes we got. Let's calculate the attribute closure of B. So B, C, D, E, F. Can we get A from here? No, we cannot get. So that's why B is not the candidate key. Let's check for C. So C, D, E, F. And can we derive anything from F? No. So B and A is not there. So that's why this is also not candidate key. Let's check for D. D, E, F and C. And from C so the whole cycle will repeat again. So that's why this is also not candidate key. Then let's check for E and F attribute closure. So they are also not candidate key. So the only candidate key we have is A. And you can see that the A is the candidate key which is atomic. So if it is atomic, there is no chance of partial dependency. So definitely it will be in 2NF. Okay, it will be in 2NF. And also in the given relation, a non-prime attribute determines non-prime attributes. So hence it is not in 3NF. Okay, so if we will check this, so A determines B. All this first of all is in first NF because the attributes are there, atomic attributes are there, so it will be 1NF. And when we calculated the candidate key, we got A as the candidate key, which is completely atomic. So if the candidate key is atomic, so definitely it will be in a second normal form. But as you can see, so as you can see, this is non-prime attribute, and this is also non-prime attribute, and non-prime attribute is deriving non-prime attribute. This violates the law of 3NF. That's why the whole relation is not in 3NF. And if it is not in 3NF, so there is no point to check that whether it is in BCNF or not. So that's why clearly we can say that option B is correct. It will be in second normal form only. Okay, let's go for the next question. Find the number of tables for given ER diagram to satisfy it is in BCNF. So the attributes, the entities we have given is E1 and E2. The relation we have between E1 and E2 is 1n, and here E2 and here R4 we have n to n, E2 and R3 we have n to n, and E1 and R2 we have n to 1, and some attributes are given. So we have to say that how many minimum number of tables we can draw. Okay. Okay. So E1 is R2 is self-referential relation it has with E1, and E2 also have self-referential relation with R3, and R4 has self-referential relation with E2. So if you will see this, if you will see R2, so let's suppose R2 has two attributes, which is A1 and A2. Okay, and here A1 is the key, and this is where it refers to. So this A1 and A2 is referring to A. So here A1 is the key and A2 is the foreign key. Okay, so if we make the relation with E1 and R2, so the attributes we will have is E1 and R2 if we combine. So attributes we will have is A, B and A2. Okay, and this A1 is the key. Okay, and A2 is foreign key. So this is the attribute we will have. So clearly from this we will have one table. Okay, one table we will have with M to 1 mapping, and if you can see this we will have a 1 to 1 mapping. So this will be one table. Okay, this will have one table. This is also self-referential R3. It will be combined with E2, so this will also have one table, and this whole also will have one table because it is 1 to 1. So you can calculate all. We will have four tables like 1, 2, 3, 4. Like one M to M will have one table, M to M will have one table, and here M to M will have one table, and here for M to 1 we will have one separate table. Okay, so likewise we did. So this whole we will have one table. Okay, so so likewise it will have four tables. Let's see the configuration, like how we will have. So with E2, if we combine with R, so it will have C, D and A, and here C will be the candidate key, C will be the primary key. Okay, and A will be the foreign key, which will refer to this, refer to this one. Okay, which will be, okay, it will refer to this, and then we will have R3. We will have the attributes C1 and C2, and this combine will form the key, and this will refer to this key. Then we will have R4. Similar, they will have C1 and C2, and again they will refer to this. So likewise, we will have four tables, which is 1, 2, 3 and 4. This is R1. With R1 we will combine. Okay, so the number of tables which will satisfy BCNF will be 4 tables. I hope you got the explanation. Thank you so much. A table T1 in a relational database has the following rows and columns. Okay, and the rows are given as the attributes given in this is roll number and marks. Roll number is given as 1, 2, 3, 4. Marks is given as 20, 10, 20, 30 and 4 is null. The following sequence of SQL statement was successfully executed on table T1. Okay, and what is the query given to us? This is the query which we need to solve. and based on that we have to find the output. So this is our whole question. So it is saying that update T1 set marks equals to marks plus 5, select average marks from T1. So let's go one by one. Okay, so update T1 set marks equals to marks plus 5. So first we have to update the marks value with plus 5. Okay, so we will do this. So 10 plus 5 we will do. Ten plus 5 here we will do. Then here 20 plus 5 we will do. Then here 30 plus 5 we will do. And null plus 5 we will do. Okay, this we will do. And what it is saying afterwards, select average marks from T1. But null plus 5 will be null. Okay, anything with null will be null itself. So we will not consider this. So null, we will not consider this. So let me write the point that null plus something equals to null itself. So what will be the value? Here the value will be 15, here the value will be 25, here the value will be 35, and here the value will be null, because null on something will give you null. Okay, now what the second line is saying, select average marks from T1. So you also have to note one point, that average function ignores null values. Average function ignores null value. Okay, so and here average function is given. So we have to calculate the marks of average, but average ignores null value. So what will be the output? The output will be, it will be then 15 plus 25 plus 35, and as the average function will ignore null, so we will count only 1, 2, 3. So it will be divided by 3, because our values are also 3, 1, 2, 3, and here we skip this because average ignores null. So that's why this will be the answer. And if we will calculate this, so our answer will comes out to be 25. So the correct option is C. Okay, let's move to next question. Consider the following table name student in relational database. The primary key of this table is roll num. So roll num is the primary key. They have already mentioned in the question. This is the PK, which is primary key. Then here see, primary key is there, so that's why here is no null value and all the values are unique. Okay, name is given, gender is given, marks are given. The SQL query below is executed on the database. So this is our database. On this SQL query is executed. So this is the query which is executed. So first we will look at from. So from is executing on the student. Then we will see where clause. Okay, so where it is F and mark should be 25. So this we will select. So condition is, first let's select female. So these are females, and mark should be greater than 65. So this is not correct, this is correct, this is correct. So 2 we have selected. Okay, so now we will run the select query. So this 2 rows will get selected. Only this 2 rows will get selected. Okay, so the number of rows entered by the query is 2, because we have only 2 rows, because 2 rows are only selected. I hope this query is understood by you all. Okay.